Modern microservice architectures process millions of parallel events per second. Every single one of those events, a user message, a financial transaction, and ad impression, requires a unique identifier so the database can track and store it. Generating these identifiers at scale presents an engineering trilemma. The system must guarantee global uniqueness. It must generate these IDs without relying on a centralized network lock, and the resulting IDs must be chronologically sortable. The legacy approach solves this by relying on a centralized relational database to generate auto-incrementing integers. Every time a node needs an ID, it asks the database for the next number in the sequence. But as the size of the cluster grows, this method fails. Thousands of parallel write requests hit the central database simultaneously, forcing it to lock the sequence table to ensure uniqueness. The central database becomes a massive throughput bottleneck. To scale horizontally, the architecture must eliminate this single point of failure. ID generation must be pushed out of the database and directly onto the individual application nodes. Relying on a central database for sequence generation trades horizontal scalability for strict ordering. For modern cloud systems handling thousands of transactions per second, that compromise is physically unsustainable. A standard decentralized alternative is UUID version 4, or Universally Unique Identifier. UUIDs eliminate the network bottleneck entirely. They allow local application nodes to generate 128-bit random strings independently, with a collision probability so low it can be effectively ignored. This chart shows a simplified B-tree index, the default storage structure for most relational databases. When a database receives sequential data, it appends the new records cleanly to the rightmost edge of the tree. But injecting pure randomness destroys this structure. Because UUIDs have no chronological order, the database cannot simply append them. It must insert each new record into the middle of the existing index, forcing the tree to constantly fracture, split, and rebalance its pages. This constant page fragmentation forces the storage engine into continuous data relocation. Write performance drops, and the physical storage requirements expand significantly because the index pages are no longer tightly packed. Random UUIDs provide decentralized uniqueness, but they degrade database insertion efficiency. To maintain database performance at scale, the identifier must be intrinsically time-ordered. This diagram shows the architecture of a Snowflake ID, originally developed by Twitter. It avoids network coordination by packing distinct metadata into a single 64-bit integer. We begin at the most significant bit, bit 63. This is the sign bit, permanently locked to 0. Locking this bit at 0 guarantees the identifier will always be parsed as a positive number in programming languages and database engines. This prevents negative value casting errors during data serialization. The next 41 bits, from bit 62 down to 22, form the timestamp block. This section records elapsed time in milliseconds. Instead of measuring from the standard 1970 Unix epoch, a Snowflake generator measures time from a custom epoch, a date set close to the application's launch. Using the 1970 epoch today would waste decades of usable integer space. Mathematically, a 41-bit allocation holds 2 to the power of 41 values. At millisecond precision, this provides exactly 69.7 years of usable lifespan before the timestamp integer overflows. By placing the timestamp in the most significant bits, the generated IDs naturally sort chronologically. When a database indexes these values, they append cleanly, bypassing the B-tree fragmentation caused by UUIDs. Next is the machine ID segment, occupying bits 21 through 12. This handles spatial uniqueness. A 10-bit physical allocation gives the system 2 to the power of 10 combinations. A 10-bit allocation gives 2 to the power of 10 combinations, allowing exactly 1,024 distinct generator nodes to operate concurrently without any risk of overlap. The final 12 bits resolve intra-millisecond concurrency. If a single node processes multiple requests within the exact same millisecond, this sequence counter increments to differentiate them. This imposes a strict throughput limit per node. A 12-bit sequence holds exactly 4,096 values. A single machine generates 4,096 unique IDs in a single millisecond. Once it hits that limit, the node waits for the physical clock to tick. To construct the final identifier in the application code, the generator does not use string concatenation. It uses bitwise left shifts to slide each value into its correct binary position, and fuses the three segments together using logical OR operations to output a single 64-bit integer. Combining 1,024 spatial nodes and a sequence of 4,096 IDs per millisecond yields a theoretical capacity of 4.19 billion transactions per second. All of this is achieved without a single network round trip. The mathematical guarantees of the Snowflake algorithm rely entirely on physical reality, specifically a strictly forward-moving, monotonic system clock. In distributed hardware, local quartz clocks inevitably drift. To keep servers aligned, networks rely on the Network Time Protocol, or NTP, to periodically synchronize local machines with an external master clock. This creates a temporal anomaly. If a server's local clock has drifted slightly ahead, an NTP update will pull the clock backward. If the clock steps back into a millisecond window where the node has already generated IDs, the algorithm will reuse timestamps. This guarantees a collision of duplicate IDs. To mitigate minor backward drifts, generators employ a defensive programming technique known as a spin-weight loop. When the generator detects that the current physical time is earlier than the last cached timestamp, the generator thread enters a defensive state. It actively yields CPU cycles, pausing execution until the physical clock catches up to and surpasses the cache time. But if the temporal regression is severe, typically greater than 5 milliseconds, spin weighting degrades application performance too heavily. In these cases, the generator must immediately throw a runtime exception and reject incoming write requests. Maintaining global uniqueness in distributed systems requires establishing defensive boundaries. The system intentionally sacrifices write availability to protect absolute data integrity during temporal anomalies. Spatial anomalies present a different challenge. In the legacy era, machine IDs were mapped to permanent physical server racks. In modern orchestrators like Kubernetes, worker nodes spin up and die dynamically based on traffic. Assigning a static 10-bit integer to a temporary container is impossible without introducing a heavy centralized coordinator, like Zookeeper, during the startup process. The solution is the stateless Snowflake architecture. Instead of relying on external configuration files or coordinators, this approach derives the node's identity directly from the physical network layer. To accomplish this, the algorithm modifies the standard 64-bit layout. By shrinking the sequence block down to 6 bits, it expands the machine ID block from 10 bits up to 16 bits. When the container initializes, the generator reads its own private IPv4 address from the local network interface. It strips the last 2 octets and writes them directly into the 16-bit machine ID block. Because IP addresses within a local subnet are guaranteed to be unique, this mathematically ensures a collision-free identity assignment. The node secures its identity instantly without a single external startup dependency. By combining structural bitwise efficiency with stateless network identities and strict temporal safeguards, the modern Snowflake architecture solves the distributed identifier trilemma. It achieves infinite, self-healing horizontal scalability while maintaining exact chronological precision.